right, so this is the last non-review lecture of the semester. Before I get started, does anyone have questions about the about Lab 4? Okay. I've been discovering this semester how depressingly easy it is to solve, typical labs using Copilot. So, you're not supposed to do that, although, there's no way to catch you. And if you did, just remember that the, the material, the things you're solving in Lab 4, you're responsible for on the exam. So if you did use Copilot, I'd suggest walking through the code and actually maybe running it in the debugger and figuring out what on earth it's doing. All right. So today we're going to talk about virtualization. So in particular, all semester long, we've been running virtual machines on our laptops. And the concepts we've discussed in class so far are not enough to describe how that works. Because, an operating system kernel, it turns out, if you take the actual kernel executable file, it's just an executable file like any other one, whether it's, for Linux or Windows. I'm not exactly sure how Mac OS boots, but I'm sure it's fairly similar. And, it gets loaded onto the computer and it runs it. The difference between that and a regular program is that it gets loaded onto the CPU in supervisor mode. The kernel has supervisor mode, and the CPU has these two modes, supervisor mode and user mode. And just about everything runs in user mode, including a lot of things that we think of as part of the operating system. But the core of the operating system is the system call and interrupt handlers that run in supervisor mode. In particular, this has things like, this is where we do things like manipulate the registers that control the page table hardware. We can't let, if you accidentally use a string as a function pointer and, start executing random instructions, and we don't want it to be able to, modify the virtual memory mappings and, and access the operating system or someone else's process. Or for that matter, if you very carefully craft some malicious instructions and try to execute them, we don't want that to happen either. So if you were to run an operating system as a regular program, it could execute for a little bit, but the first time it tried to execute a supervisor mode only instruction, it would obviously fail. So clearly, your virtual machine isn't running as a regular Mac OS or Windows process. I'm going to explain a, well, let me back up. Before I explain how it gets done, I'll I'll explain why. So, actually some of the earliest, well, virtualization got a lot of, a fair amount was written about it, and it got a lot of, attention back in 1970 or so, and then in the late 90s. In the late 90s, it was first, like when VMware first started, they were doing kind of what we're doing now. People wanted to be able to run Windows on their Linux machine, or they wanted to be able to run Linux on their Windows machine, or things like that. And that's sort of what motivated them to do it. So a while back you might have run Windows in a virtual machine on your Mac to get access to certain software that wasn't available for the Mac. So this is sort of, I would say it's sort of the hobbyist use of it. I've got my computer here. I want a different OS, but I don't want to have to reboot everything, so I can load this virtual machine. What they soon discovered was that the big use case for virtualization was server consolidation. That, for various reasons, a lot of times you need an entire server for a particular application. Maybe because it's answering port 80 as a web server, and there's only one port, port 80. Maybe because it's uses the certain libraries and operating system versions and so on. But the vast majority of applications, in fact, did not fully use their servers. I can remember seeing server rooms in 1995 or so where I would bet that most of the machines were about 5% utilized. Because you've got a print server that if nobody's printing anything, it's not doing anything, stuff like that. So if you take a bunch of physical machines and you consolidate them into virtual machines running, on much less hardware, that's a big win. That saves somebody a lot of money. That saves someone a lot of money even after VMware increases their prices so that they capture maybe half of that savings. And they were able to charge an awful lot for the software that did that. Okay, so, and then an even bigger use case later on was cloud computing. So I can remember long ago there used to be a company in Brookline in like the early 90s that you could pay them and get a dial-up account on a Unix machine. And they had various message boards, and you could sort of access the internet such as it was back then. That was pre the World Wide Web protocol hadn't been created yet. But having a bunch of people share the same machine is is not all that useful. The reason that you could have people share a machine in a department or something like that is because you had a single system administrator. Um, People could make decisions about what software was going to be installed, and that way you could actually get useful things done. If you're running a system with random people, random users who gave you a credit card, that range of applications is going to be very narrow. Again, email, bulletin board, stuff like that. You're not. It's a very bad model for for selling computing service. At least selling it for anything more complex than that, for internet-facing applications or things like that. When Amazon Web Services began in 2006, their third, they very rapidly introduced a queuing service that no one remembers but is still around, and then S3, and then EC2, which is their virtual machine service. And so you can get a virtual machine, you can fire it up, you can administer it however you want, and basically you get one of these virtual machines on a piece of hardware with its own file system, its own user IDs, its own virtual network interface, in fact, its own virtual disk. And you can destroy whatever you want because the only things you can touch are in that virtual machine. And whoever, if some bad guy happens to have another virtual machine on the same hardware, it's going to be very difficult for them to do anything to you that, or at least anything that they couldn't have done just coming in from outside over the network anyway. So, I've mentioned it a few times that essentially the reasonable unit of computing is usually bigger than just a process. You want to be able to install things. I don't know, has anyone used virtual environments in Python? Okay, that's an example of people have gone to considerable lengths to handle the fact that you may want a bunch of a particular custom installation for something. In that case, you can create an installation environment for your Python project, and you can install various things into it and use that, and then but it doesn't mess up the overall system configuration. Most software isn't that polite and doesn't have mechanisms like that. All right, so virtual machines are useful. What are they? Well, essentially, what a virtual machine is I think I've mentioned before, you can look at a process as a sort of virtual machine. It gives you this very clean virtual machine that has the user space registers, the user space instructions, and then this system call mechanism. And so everything beyond everything beyond what you're computing in your program is handled by some sort of system call. A virtual machine has, memory, page tables, interrupt handlers, timer interrupts, disk controller, disk blocks, a network interface, all the things that an operating system sees in the hardware underneath it. Um, at first, in fact, it was quite important to truly emulate that real hardware because you wanted to be able to do things like install Windows from an official CD-ROM. And if you weren't emulating hardware that OS supported, then that wouldn't work. So I'm going to explain a series of increasingly complex and increasingly higher performance ways of implementing virtualization. So the first is basically lab one. You add basically you just sit down with the the vendor's manual for the particular CPU, and you start extending that program so that it tracks not just 8 registers like we had before, but whatever the registers are in that CPU, the supervisor mode, the special registers like the page table route, interrupt vectors, things like that. You'll on every memory access, you'll have to emulate the memory management unit. Look the address up in the TLB or in the page table. You'll have to, when you're accessing the address, you'll have to check and see, is this real memory or is this actually a hardware device? If it's a register on the network interface card, well, you'll have some logic that emulates the behavior of that card when you write to it and read from it, and so on. It's, conceptually, it's relatively straightforward. In practice, yeah, it'll take you a long time because there's so damn many instructions and special registers and so on. But you can go through this and make it work. In fact, the earliest Intel CPU that could run Linux or other, that had a proper user supervisor mode and support for address translation was the 386. Someone has written an emulator for the 386 in JavaScript, and you can boot an early version of Linux in your browser. Granted, that person is, crazily good at what he does. I don't expect someone else could do that, but it's just a matter of translating every instruction, and in that case, for instance, picking a simple enough CPU to make it a little bit easier. So I won't go into a lot of detail about, the hardware emulation here. Just, for instance, for the disk controller, once you figure out that it's reading or writing a block, you can just have code that writes to a disk image file, or reads from it, just like we're doing in Lab 4. For the network, you can, you can send packets out and get them back in and use a separate address for your virtual machine. Now, what would the downsides of this approach be? Why might you not want to use it for something like server consolidation? How fast do you think this runs? Very slow. Very slow. So it's not going to be much good if these machines are each being 5% utilized if they're running 100 times slower when they're on a virtual machine. So it can be a very accurate emulation. It's cross-architecture. I mean, that Linux in a web browser is an example. There, it's in JavaScript. It runs in anything JavaScript runs on. But, typically, it'll be written in C and be able to run on anything that, or a language like that. You can just compile it on whatever machine you want. In fact, if you're developing code for small devices, you may actually do a lot of your work with something like this. If it's a, years ago, well, cell phones aren't a good example now because now they're very powerful computers, but still, if you're developing, your toaster or microwave or something like that, you're not running your compiler on the machine that the code is going into. You're not running a debugger there. Instead, you'll do most of your development with an emulated environment. I would bet that a lot of automotive and electronics are like that, and things like that. And it works great if your development environment is, enough times faster than the real CPU. Okay, so this is so people doing Java and other interpreted languages call this JIT, just-in-time compilation. The virtual machine folks have always called it binary translation. But the idea is that you can accelerate this by dynamically translating code, binary code. So if I have okay, if I have a single instruction here, move R1 to R2, this is going to have to If you remember lab 1, if you had an instruction that copied a value from one register to another, you would have, R sub 2 equals R sub 1. And that's going to translate into instructions that load a real CPU. The compiler will generate instructions to load a CPU register from the memory location that's holding our emulated register 1 and store it where our emulated register 2 is. And then okay, but if you remember lab 1, there's this whole loop overhead of fetching the instruction, figuring out, parsing the parts of the instruction, figuring out which one it is, and so on. So I can actually translate this. What I can do is at runtime, every once in a while, I'll look at the code that I'm executing right now, and I will translate it into just and then um, and the thing is that as I start doing this to a few instructions at a time, I can start optimizing. I can take a second pass on it with what they call a peephole optimizer and say, oh, I loaded this variable, our emulated register 1, into a register. So I don't have to read it back again. I loaded, so in fact, if you translate a chunk of 5 or 6 instructions or something, you can translate it into a sequence of real hardware instructions that's a lot faster than just implementing each instruction once at a time. So not only have we gotten rid of the loop overhead, but we've gotten rid of a lot of the emulation overhead. So in a good implementation of this, we would be able to, this might be 3 times as many instructions as the original code. So, that gives us, a 3x slowdown or something. If you have really good people, maybe you can do better than that. And so this is how, this is why Java works. Java it compiles to a bytecode, which is basically a machine language. Well, it is a machine language. It's for, a sort of generic CPU that has certain instructions. And, the Java interpreter starts out reading each instruction and interpreting it, but then it starts taking chunks of them and translating them. And then when it reads each instruction, it checks to see, have I translated the code at this address? If I have, I jump directly to that code, execute it, and jump back. Otherwise, I keep interpreting. So this is a lot trickier to do, but so. Well, so as an example, Apple has used this approach multiple times when they've changed CPUs. So if you look at the activity monitor, if you have a Mac, you might see that some of the processes running say that they're Intel. They're actually running on the CPU from the prior generation of machines, and they're using a mechanism like this to do it. When they released the original Intel CPU, Intel machines back in 2006 or something like that, they had an emulator that let you run binaries for the previous generation of PowerPC CPU-based machines. There's also a program called QEMU on Linux, which emulates different CPUs that way. And then, you also, I guess one reason why this doesn't translate so, one-to-one is because you have things like you may have to translate addresses. You may have to, do other things like that. Although again, if you have several instructions in a row, once you've translated an address, you can realize that you're using the same address, say it's a pointer to a structure or something that gets used in multiple instructions. Well, if you translated it for this instruction, then you can keep the translated address and keep using it. So with a bunch of subtle software, you can make this run a lot faster. So it's still not fast enough if you want to be in the business of selling virtual machines. 2 or 3 times slower means that you're throwing away 50 or 67% of your machine. You'd rather not throw it away, you'd rather charge people for it. So So the next approach requires that you're running on the same CPU architecture, which is fine. I mean, that's why if you've got a Windows machine with an Intel CPU, you have the Intel VM for this class, or if you have one of the few remaining Intel Macs, and the rest of us have, ARM64 virtual machines on Apple Silicon. In each case, we're running a virtual machine that is executing the same instructions as the underlying CPU. So there's no need to translate instructions. We just have to handle this whole pretending to have user supervisor mode when we're not the OS. So well, first of all, let me draw a picture. So we're going to have three different levels here. We're going to have multiple virtual machines running on top of a hypervisor. So years ago, IBM called their operating system supervisors, and then they invented virtualization, so they needed something that supervised the supervisors, and it was the hypervisor. So this is it's like an operating system, but instead of providing processes that give us our familiar programming environment, it provides virtual machines which pretend to be, an entire hardware machine. And then in each virtual machine, you're running a guest operating system, which thinks that that it has user and supervisor mode available. And then you have applications that run in user mode. So the So what we're going to do is we're going to have an emulated CPU for the virtual machine that has, all the registers, including the supervisor only ones, page table, all that other stuff. And we're going to So what we're going to do is we're going to just run the OS in user mode. And then eventually we'll hit a supervisor mode only instruction. We'll get an illegal instruction fault, and that will jump into the hypervisor. At that point, we can copy all of our real hardware CPU registers into our emulated CPU. And update the program counter in the emulated CPU and so on, and then we'll emulate a single instruction. And then we return back and we keep running in user mode. Or maybe we'll get an exception here. Maybe our supervisor mode only registers say, oh, the emulated CPU isn't in supervisor mode, so I should call, instead of returning there, it will set the program counter to the address of the illegal instruction handler and start running there. Or it will basically do whatever the real hardware CPU would do if it was in that state and ran that instruction. And so basically your supervisor mode only instructions are going to be emulated one by one, but every other instruction is going to just run on the native CPU. So that means when you're running your applications, well, there's not going to be any virtualization overhead while your app is running because it's in user mode. It's not doing any of these things. When you go into the operating system, most of the time an operating system is running boring code. If you look at your thread library, there's one thread switch function in the middle of everything, but almost all of the code is handling lists and things like that. Is bookkeeping, and that's the case in any operating system, except that usually there's a lot more bookkeeping than there was in our thread library, and there's not all that much more sort of subtle special purpose code like these supervisor mode instructions. So if you do this, this lets you emulate. This lets you run your guest OS at near full speed. If you had, there's a few things that need to be done as well. So to emulate hardware I/O devices, where in our emulation we're going to have to look at every memory access and say, after translation, does this point to regular memory or does it point to a hardware device? In this case, our hypervisor isn't going to map the real hardware devices, and so every time the guest OS tries to access them, it'll generate a page fault. And so, the page fault code is really, the code that handles that is going to be really ugly. It's got to figure out what, decode the instruction, what value is it trying to store to what address, and then pass that to the, network hardware emulator or the disk controller emulator or whatever. But conceptually it's straightforward. It's just, there's a slog to go through to get it to work. There's the last thing is so there's a problem with memory translation because we have so the guest OS is responsible for virtual memory. It's an operating system. It's going to do virtual memory management. It's going to come up with address translation tables. The problem is that it's going to be using fake physical addresses because the hypervisor uses the same technique that the OS uses. It protects things from each other by using a translation layer so that the fake physical addresses that this guest OS is using map to memory that it's been allocated. And there's no fake physical address here that maps to memory that another VM has been allocated. It's just the same as how you protect memory between processes. Again, you know, process one, if memory is allocated to process one, you install it in process one's translation table and not process two. So the hypervisor has to manage this translation. Unfortunately, we've only got a single set of page tables. So once again, we fake things out. The hypervisor, well, the guest OS, its supervisor register is pointed at, you know, its page table register is pointed at a fake page table. And then when the hypervisor gets a page fault, it looks in the fake page table, and if it turns out that the guest OS thinks that it's already mapped that page, well, it takes the address, the mapping from here, it applies this mapping in software, and it installs it into the real page table. If it's not there in the fake page table, then it's a true page fault, and so the hypervisor will just call the, you know, the emulated, the OS's page fault handler, you know, like real hardware would. And so this technique was discovered in about 1970, and IBM thought it was the greatest thing. For years, a lot of their systems ran what they called VMCMS. You had virtual machines, and you know, you were, as a user, you were given a virtual machine, and it ran CMS, which was some sort of single user operating system inside of that virtual machine. I don't know much about that other than how it's spelled. It's before my time, and there's also this big gap between people who, you know, between people in sort of the engineering world and people in the IBM world. So there's one problem, though. Or rather, this worked fine for IBM for many years. And in fact, they added several, you know, they made some modifications to their computers to be able to handle this more efficiently. I seem to recall that they had an instruction which would say, execute the instruction at this address. And it would go do that. And, you know, it had things like that. The problem is that what get called non-virtualizable CPUs. So in particular, the easiest example is, what if some of the instructions don't that you need to virtualize don't trap in user mode. There's some number of CPU architects have, when they've defined their CPU, have thought, oh, it doesn't make sense to do this in user mode, so we'll just make this a no-op. If you run this command in user mode, it won't do anything. Whoops, we can't use trap and emulate virtualization, because you can't trap and emulate if it doesn't trap. So what are some non-virtualizable CPUs? Well, only the most widely used CPUs on the planet. So in the later 90s, when the VMware folks were trying to, they had done some research stuff on other machines, but they wanted to do virtualization for Intel CPUs. They were stuck with the problem that you can't apply the traditional virtualization approach to an Intel CPU. So the first solution, the solution that they went with at first, was to when you went into supervisor mode, whatever you did would trap into the hypervisor, whether it was an interrupt or a system call or a page fault or whatever, and the hypervisor would just stay in emulation. It would just emulate everything in supervisor mode until you returned back to user mode, at which point it would stop emulation, jump back to the real code, and start running at full speed. So this slowed down, well, this didn't slow down user code at all, because again, because once this guest OS returns back into the application, the hypervisor would realize, okay, we've turned off supervisor mode, now we can jump directly to the code and start executing it. And now, the hardware CPU would be executing your code at full speed. But when you go into the operating system, that code is going to be emulated and it's going to run slower. In practice, this mostly affected networking applications, because if you were doing a lot of disk access, well, there weren't a lot of instructions in the path of reading from the disk, and you'd spend time waiting for the disk and all that. Whereas all the code to process the network protocol is usually pretty fast, but you slow it down by a factor of 2 or 3, and it starts taking more time. But it does work, and it can work quite well. In fact, they were able to do a bunch of really fancy things with this just-in-time compilation, like recognizing the instructions that wrote into the page table and doing special stuff with them, or recognizing the instructions that we're writing to a hardware device, and translating them differently, and so on. So that works pretty well. People spent a lot of effort trying to come up with an alternate way, mostly because they put a patent on it. So okay, so the thing about this is this lets you implement something that is, other than performance, is exactly like classic virtualization. You can emulate every piece of hardware in the computer. It might not run as fast, but if your OS writes to this physical address, it will cause this emulated register in your network interface card to get written, things like that. You create a page table, the same code that updates your page tables and invalidates TLB entries and so on. When your OS is running on bare metal hardware, is going to work perfectly when we run it in a virtual machine. What paravirtualization does is said, wait a minute, do we actually need that? For a lot of applications, we don't. Think about your Amazon virtual machine. What matters is that it's a virtual machine. You're not trying to load, a Windows 98 CD or something like that. You want a Linux machine that's running separate from everybody else's Linux machine. So what we do is basically the hypervisor, a paravirtualized hypervisor, is an operating system for other operating systems. So instead of having functions like open file and close file, it has it has a bunch of system calls like this. Oh, that that you that that replace the hardware functions that the operating system uses. And this takes advantage of the fact that just any modern operating system, certainly Linux, if you look at the Linux source code, there's this /arch directory containing architecture support for different architectures. There's probably 30 in there now. And for each of them, there may be variants. And they have specific functions and macros for updating page tables, for installing interrupts, things like that. And those are structured in a way that if you want to have the operating system run on a different piece of hardware, you can you have to figure out how do I, you know, how do I implement the operating system page fault functions, or, how do I implement the page table update functions or other things like that for this specific hardware. And normally that involves looking at, the at the data, at the manual for that CPU, figuring out the page table formats, doing things like that. If you look in the Linux source code under x86, there's a subdirectory called Xen, XEN, for this paravirtualization system. And those things translate not to specific CPU instructions, but to hypercalls, to these hypervisor system calls that install page fault handlers, add a page to an address space, switch between two address spaces. And it wasn't that much work adapting Linux to use that interface. I'm sure it was considerably more work creating the hypervisor itself than making the modifications to Linux. They also modified a particular version of Windows and were able to run it over that. They were at Microsoft Research at the time. And so that gives you a totally alternate approach where the guest OS always runs in user space and it never tries to execute supervisor mode instructions. Instead, in the same way that your code doesn't execute supervisor mode instructions, we ask the OS to do it through a system call. With paravirtualization, the guest OS asks the hypervisor to do this supervisor mode stuff. This turns out to be quite efficient. It's among other things, in trap and emulate, there's a whole bunch of places where you find yourself basically disassembling instructions and trying to figure out, the interface to everything is instruction disassembly. We have a page fault because you wrote to the Ethernet controller. Well, we have to disassemble the instruction, figure out which register you were writing, get that register from the saved registers, pass it to our emulation function. Here, you just pass arguments to the system call, to the hypervisor call. In fact, this is the approach that Amazon took in their first virtual machines because they didn't have to pay anybody and it was quite efficient. And to this day, they, if you ever, if you Google for, AWS announcements about PV virtual machines, you'll find that, they're deprecating them, but clearly they've got significant customers that still rely on those, almost 20 years later, because they continue to support, various new features on them, just not the latest ones. Now, there's a third way we can do this. So, it's been close to 30 years since people have been widely using virtual machines. And in that time, the hardware vendors sort of figured out that people might want to do this and that they should modify their CPUs to do that. In particular, I think it was mostly driven by AMD around the time that they were developing their 64-bit extensions. Intel was off on the, Intel had decided they had a CPU of the future that was radically different. They spent billions of dollars on it and it flopped, so they weren't really paying attention. So AMD went and developed 64-bit extensions to the Intel instruction set and a set of virtualization extensions. So the problem is you already had user mode and supervisor mode, and you couldn't just change the instructions so that the right instructions faulted at the right time. For a couple of reasons. One, because it would break everybody's existing code. Another was because some instructions had been defined in a way that you just couldn't untangle them. You had some instructions which did some supervisory things and some non-supervisory things. And if you use them in supervisor mode, they do all of the things. And if you use them in user mode, they do half of those things. It turns out one of those instructions was for, checking a status register that told you if, an integer addition had overflowed or something like that. An instruction that, happens all the time. So they couldn't even just put a trap on it because the overhead would have been unacceptable. So what they did was they added a third mode to the CPU, and they had the supervisor mode instructions trap into hypervisor mode. In fact, there's a whole bitmap you set up to decide which instructions trap depending on how you designed your hypervisor. And then you can emulate those instructions, in the hypervisor and then return back to the supervisor. And so now we're back to being able to do trap and emulate. It's worth pointing out that this is one of those cases where, there's a lot of things in computer architecture where someone will say, oh, this solves it in hardware, and that doesn't always mean it's faster. It's nowadays, yes, this is faster, but when it was first introduced, it actually wasn't faster. However, it was vastly easier to program, so various other companies could come up with their own hypervisors and virtualization systems and so on. That's how VirtualBox came about and things like that. The amount of effort necessary to do something like that, never mind the patents that were in force at the time, would have kept someone from doing it with binary translation. There's a few additional things that have been added on over time. So I mentioned how the problem with handling address translation with virtualization was that you only had one page table and you wanted to translate, you wanted a two-step translation the first step managed by the guest OS, and the second part managed by the hypervisor. Well, modern CPUs have two page tables. And so this is there's, if you read other textbooks or articles about virtualization, there's a couple of different words that get used for this intermediate address, whether it's a physical address and this is a bus address, or other things. It's easier to just say this is the fake physical address and this is the real physical address. Is there anything else? It turns out that they've added, well, it turns out that you can also use this setup to map hardware devices into the guest. And if you do it right, the guest will be able to control DMA adapters and write to the registers because they've been mapped into the guest's fake physical address space. And the device will be able to DMA from that memory and so on. So, there's been a number of things done to make this more efficient. Certainly when we're using VMware Workstation or Fusion, I'm pretty sure it's using hardware virtualization and hardware memory virtualization, in the default parameters. All right. So actually, it turns out just about every so it turns out that paravirtualization is actually great for emulated devices. You can have a hypercall that's, send this network packet. Here's a pointer to it. Here's the length. Write this block to the disk. Instead of taking a page fault, decoding an instruction, doing that several times while you write to registers, you just make something like a system call. Now, the thing is that we can use paravirtualized I/O without having to, modify the OS, because pretty much every OS has mechanisms to modify it to support new hardware. You just load a device driver. So, sometimes it's loading the guest tools extension or something like that. But what that's doing is installing, paravirtualized disk and network drivers. So they'll use a particular exception, for instance, and as a system call into the hypervisor, and pass a set of arguments, and so they can, very, that makes it very efficient to, um, to do I/O compared to, as I said, emulating access to the real hardware. And since, as I said, it's not that you're not modifying the OS, it's that every OS has the, ability to easily add new, support for new devices. So for a virtual disk, the easiest way to do it is you just have a single disk, a single file. If you want a 10 gigabyte virtual disk, you create a 10 gigabyte file. You read from, to write a block, you write to that offset, the right offset in the file. To read a block, you read from it. There's a lot of effort. So a lot of effort has gone into, formats for these virtual disks, partly because you don't want to use up, you'd like to have, a disk image that's large enough if you have a bunch of data on the virtual machine, but until you do that, you'd rather it not eat up all the disk space on your computer. So you'll have some sort of sparse format. So essentially, if you think about it, when you write a block to it, it'll have a map like a page table. When you write a block, it'll allocate some space, put something in the page table, and write to it. And so if you write, to 5 or 6 random locations in your 20 gig disk, I'm not sure what Fusion and Workstation use, but if it were VirtualBox, it would allocate a 64K chunk for each of those, and that would be, plus another, few 64K chunks for the, file, for the mapping table and stuff at the top of the file. And that would be the extent of how much data got stored on disk. Not only that, but with a bit of extension to something like that, you can support snapshots. Kind of like what I described with copy on write file systems. You can set something so that, if you try to write, basically you make the entire virtual disk read-only, and every write is going to copy that section, that small block, into a new location. And so now you can, for instance, you can take a snapshot of your virtual machine, and if later on you want to go back to that snapshot, you just, bring up the snapshot window and go back to it. Now, a lot of my research recently has focused on remote disks for virtual machines, because you've got a whole bunch of computers, and you're running virtual machines on each one of them. And at some point in time, some of these machines are going to fail. Now, if your laptop fails, well, you take it to get fixed. You maybe see if you can recover the disk, things like that. But when you're running 10,000 machines in a data center, some of these machines are going to fail in ways that you can't recover. Occasionally one will probably catch on fire or something, equivalent. So you would like to be able to not lose data in the case that that happens. In particular, you'd like to not lose your customer's entire virtual machine. If I don't know, if you dropped your computer on Huntington Ave and it got run over, you would lose the virtual machine on it along with everything else. But here, what we do is we have a virtual disk. We have another big pile of hardware implementing virtual disks. And we connect, and the hypervisor connects to that virtual disk over the network. Now, if this dies, well, that's kind of like if you had a power failure with a desktop computer. You just boot the virtual machine up again on a different machine, and you're good. And so this is, in particular, this way of using virtual machines was originally developed not as much for cloud computing as a few years before that, for having very large internet systems that kept running, that were very reliable. Because you could have 1,000 or 10,000 virtual machines implementing Amazon storefront or Google search, and if something failed, well, it could be brought back up again on another machine. If we wanted to replace a rack of these machines, we could shut these virtual machines down and boot them up again on other machines. So we wheel in a new rack of machines, shut the VMs down and boot them up on the new ones, and now we can take this away to the recycler or whatever. So it turns out that, in fact, I'm not going to describe it, but there's ways that you can move a virtual machine. If you're using a network virtual disk, you can move a virtual machine from one physical location to another, one physical machine to another, without stopping it. There might be a hiccup for 1/10 of a second or something like that, that kind of like a network glitch, but it will keep running. So you can have a virtual machine that runs longer than any of the hardware in your data center. It's kind of like, eons ago, I remember asking someone I was working with, why are we buying these servers that have 2 power supplies? I've never seen one die. And they said, oh, it's nothing to do with that. You can take 2 extension cords and you can leapfrog them and get from one room to another without ever turning the computer off. It turns out you can do that with virtual machines now. You can have it move, from one place to another and never shut down, even when your hardware does. The last thing you can do with these disks is I mentioned how, if you took a snapshot, then any modifications you made would get written separately and not not change, the snapshot. Well, what if that snapshot was say an Ubuntu image provided by, the cloud provider or something like that. You can have, in fact, most systems provide, various, um, prepared images that you can start a virtual machine with, and that are fully installed, and you just boot it up, and any modifications to the disk are in the, so you're basically cloning that disk, and the clone has all the modifications you made, but which build up over time, but you started out with this golden image. Um, and so this, in fact, has been very useful for cloud computing, because it's much easier to start up a system um, from a known booting image. It's the same reason they install the operating system on your computer before you buy it. So, all right, that is my my virtualization lecture. So we talked about going from software emulation to software emulation plus, JIT or binary translation, to trap and emulate, to handling non-virtualizable CPUs with either full binary translation for supervisor mode or hardware extensions. We briefly talked about, both the hardware and software ways of memory virtualization, and talked about virtual disks. And and we talked about paravirtualization. So questions before I finish it up? Yes. Okay. Basically, instead of running the kernel in user mode, we run it in supervisor mode. So, when it checks, it sees, when the page fault handler checks to see if it's in supervisor mode, for instance, which is a typical thing to do, it sees that it's in supervisor mode. And, and then when the operating system tries to do one of those privileged instructions, because we have hypervisor mode turned on, instead of just doing it, it traps into the hypervisor. So the hardware vendors were able to make those instructions trap into a third mode, when you turn this function on, and that didn't break anything. It would have been a problem if they had changed the way they worked across the user supervisor mode boundary. That's all your programs. So, so 99% of the time, the CPU is running your code. It's not in the OS, and so that's and that's one reason that virtual machines can be pretty efficient, is because the stuff that isn't all that efficient is things that don't happen very often. So, all right, so Tuesday is going to be a review for the final. The final will be, like the midterm, handwritten notes. It's, similar. You will see the, CPU compiler question again. Please get it right. But it's weighted towards the second half of the semester. And, and good luck. Yes. Yes, from the file system homework. I will get the solution to that out as soon as it's, and there's another solution pending, I think. I'll get that out, as soon as possible as well. Yes. If you look in Canvas, I gave you all 5 for homework 7 because I didn't get it out. That seemed the fair way to deal with it. Other questions? Okay. Yes. Yeah, yeah, I would say. Yes. Yeah. Um, I'll post something on Piazza. I don't think there's time for me to get a homework out on the permissions, but Unix permissions will definitely be on the test. I would have done a file write homework, but again, was late, so that won't go on the exam. Um, and there's one or two things that got bumped because we were focusing on the CPU and compiler thing. So, all right.